Hi everyone, welcome back to Dave's Math channel. Today this is my second video in a series on limits, which is a sub-series of calculus. So today I'm going to talk about speed. I think you guys all kind of know what speed is, but it's actually more complicated than you might think. And the whole notion of speed actually does involve calculus. And I'll explain that as I go on. So let's just start. Let's start with something simple. Imagine, this is probably how you learn how to calculate speed. Say you're driving a car, so you're driving a fixed distance at a constant speed. So you're driving, I don't know, 50 kilometers per hour, and you drive for 1 hour. Well, then obviously the distance you're going to drive isn't going to be 50 kilometers, and usually that's how you define speed. If you're traveling 50 kilometers in 1 hour, then your speed is just the ratio, if you like the quotient, 50 distance divided by time. So if your distance is 50 kilometers and your time is 1 hour, then your speed, if you're going a constant speed, is 50 kilometers per hour. If you're driving 100 kilometers in 2 hours, then you divide 100 by 2, you still get 50 kilometers per hour. So you get the idea. That's probably how you first learned about speed. But this definition really isn't that good because it's assuming that you're driving at a constant speed, and obviously you don't have to be driving at a constant speed. But I'm just bear with me a little bit more. You probably learned all this too. This is kind of a useful triangle. I don't know if you guys ever learned these triangle diagrams, but it's kind of nice because if you look at the positions of distance, speed, and time in this triangle, you can just see the distance is on top. Distance is equal to speed times time. If you want to calculate speed, it's just distance over time because distance is on top, times on the bottom. If you want to calculate your time, it's just distance divided by speed. Kind of a nice mnemonic for remembering all these formulas. And you can do this with any ratios you want. I just think it's kind of a cute trick. Um, but like I said, this formula is only useful if you're moving at a constant speed. And the table on the left shows an example involving constant speed. Here we're doing meters per second. So imagine we have an object moving at 6 meters per second. So then, if you know its a position, if you know, then you know exactly how far it's going to move in every time interval. If it's moving at constant speed, obviously, after 1 second, it's moved 6 meters. After 2 seconds, it's moved 12 meters. So on. Position, if you like, displacement or distance, which usually uses right as d or as s is equal to speed. I guess they're writing this, or no, they're writing, yeah. So we write time as t. So if you use ds and t, d is just s times t. Yeah, so that's all you do for the table on the left. But the table on the right is more complicated. Look at this one. We're no longer moving at a constant speed, right? You can calculate your average speed if you like. So in the first second, we've moved 1 meter. That means your average speed for that first second was 1 meter per second. But what about after 2 seconds? Now you've moved 4 meters in 2 seconds, so that's going to be 4 divided by 2. That's going to be 2 meters per second. So that means your speed is increasing. Your average speed for the first 2 seconds is more than it was for the first second. Similarly, this is quadratic. You can see 9 divided by 3. The first 3 seconds, your average speed was 3 meters per second. And for the first 4 seconds, your average speed was 4 meters per second. This is an example involving what's called a constant acceleration. I'm not really going to talk about acceleration in this video, but acceleration is just the rate at which your speed is changing. So your speed doesn't have to be constant. And then, so really, what you really need when you want to really define speed properly, you have to talk about what's called instantaneous speed, because speed can vary, obviously, like the example I just showed. And I think we all have kind of an intuitive idea about instantaneous speed because when you're driving, you have a thing on your car called a speedometer. That's exactly what your speedometer is measuring. It's measuring your instantaneous speed. So at every instant, we kind of have this notion that at every instant, every moment, your car is moving at a particular speed. And that doesn't mean you have to calculate distances and time intervals to get that speed. You just kind of have a feeling about how fast you're moving, right? I mean, imagine you're out with your friends. Maybe you're getting a little wild, and maybe your friend's driving at 90 miles an hour. Well, you don't have to wait a whole hour to see that you've driven 90 miles, right? You can kind of see that you're going really fast. Maybe you're passing up all the other cars on the road. I mean, we all have a feeling about that, right? You're driving too fast. Your friends would be scared, and they'd see the speedometer says 90 miles an hour. But even if they weren't looking at the speedometer, they still probably know you're driving too fast. So I think you kind of get the idea. So your speed can vary. And here's a graph. This is a graph of speed versus time. And your speed doesn't have to be constant. As a matter of fact, most of the time it's not. I mean, imagine you're just driving to the grocery store. You imagine you live in a big city where there's a lot of traffic, and say there's a grocery store that's 5 miles away from you. It might take you a half an hour to get to the grocery store. That means your average speed was only 10 miles an hour. But, there's probably stretches where you're driving 25 miles an hour where there's no traffic. And then there's other stretches where you're stuck in traffic. You might be driving 0 miles an hour part of the way. So I think your profile would kind of look something like this, right? This is a pretty typical profile if you were driving in a big city and just trying to get around. So obviously your speed can vary quite a bit. But what do we mean by instantaneous speed? We still haven't defined that. Well, here's where calculus starts to come into play. So here's what you're supposed to imagine. This is a measure of so we can measure average speeds, right? We know what an average speed is. We just take two times. So here we call them t. That's our first time, and then our second time we call t plus delta t. Delta t is what's known as a time interval. Delta always refers to an interval. So imagine your t. Say t is 0. I mean, t can be whatever, but say t is 0 seconds, and say t plus delta t is 1 second. So say that at t equals 0 seconds, say your speed is well, s. I guess they're using distance here. Yeah, s is distance. So say you've already traveled 40 miles at t equals 0. You can define your origin of time whatever you want, but then say, and let's not make these seconds. Let's make them hours, I guess. So say after 0 hours, you've traveled 40 miles around along a highway, and then after another hour, you've traveled 100 miles. So and then obviously your average speed is 100 minus 40. That's your delta s. That's 60, and your delta t is 1 hour. Now that's a pretty long time interval, but you notice if you look at this graph, your speed wasn't constant. I mean, it looks like your speed was 0 when you started out, but then you started accelerating. So maybe by the time you're done, you were actually driving 120 miles an hour. Your average speed was 60 miles an hour. So how do you calculate instantaneous speed? Well, the idea is you're supposed to let these delta S's and delta T's get smaller and smaller. So I think the next slide kind of shows this. So you have to, I mean, the way you were calculating these average speeds is you're actually calculating the slope of these chords. These are called chords. So look at the red chord. Here you've got T1 and T6. These are pretty widely separated times. These times could be separated by, say, I don't know, say, I don't want to go by hours. Hours is a long period of time. Let's do minutes. So let's say T1, T6 minus T1 is 5 minutes. So this red line would show your average speed over a span of 5 minutes, your average speed between T1 and T6. Well, that doesn't really capture your instantaneous speed very well because your speed was increased was a lot faster at the beginning of that interval, and it was actually negative at the end of this interval. Um, so anyway, let's look at some other chords. And then let's look at the green chord. So the green chord is going from T2 to T5. That's a smaller time interval, and you can see this one has a smaller slope. Um, and you can keep going. You can keep converging. And say you want to know your speed at t0. Well, in this case, your speed at t0 is 0. It's just a slope. So the idea, it didn't have to be 0. Maybe this was kind of a bad example. But the way you're supposed to think of instantaneous speed is just the slope of what's called the tangent line. The tangent line is the line that these chords approach as you approach a particular time. So going back to this previous slide, imagine that you're taking chords. They don't show it here, but here's a blue chord. So let's say you're getting closer to another point. So then you can move this blue chord closer and closer to the curve. So you wanted to calculate your speed at some particular time along this green curve. You can move it closer and closer to that point. And if you do that, you'll eventually you'll get to what's called the tangent line. That's the line that's just touching the point on this curve, and then that'll be the slope of the tangent line. That is what's called the derivative, and so speed is a derivative. It's just the slope of the point on the curve. That's how you define instantaneous speed. And so anyway, yeah, here's an example where they actually show a tangent line. And, it's this red line here. It's a tangent line to the point that's touching it on the graph. And you can see this has a positive slope, which means the instantaneous speed at this point where the red line meets the curve is positive. That means you're moving forward at that point. But there's other points on this curve where you're moving backward. So that would be a negative speed. Actually, there's no such thing as negative speed. This is really velocity. Velocity involves speed and direction, but I didn't really want to talk about velocity today. But if you're moving in one dimension, it's not hard. It's just either positive or negative. So anyway, and then you can do some kind of interesting things. Once you have a notion of instantaneous speed, you can calculate distances using average speeds over different spans of your trip. So here you're moving at constant speeds in different time intervals. So notice that the red line on this curve, these are all line segments. The red line segment goes from 9 a.m. to 11 a.m. And notice that you've moved 30 miles. You've moved from a distance from 0 miles to 30, or kilometers. You move from 0 to 30 kilometers in 2 hours. That means your average speed in that span of your trip was 15 kilometers per hour. But then notice the blue line, that's horizontal. So that means that your average speed during that interval was 0 because you didn't move, right? You didn't move from 11 o'clock to noon. You were stationary. Maybe you were parked. Maybe you were out getting lunch during that period of time. But then imagine your next part of the trip from 12 to 12:30. Here you're driving pretty fast. Here you're going from 30 miles to 60 miles. You're driving or 60 kilometers. You've driven a total of 30 kilometers in just a half an hour. That's an average speed of 60 kilometers per hour. And that's a slope. You can see that these speeds I wrote down here are all just the slopes of these line segments. And then for the last part of the journey, maybe you're returning home. And then your speed is negative because remember, I'm doing one dimension. You can imagine you're moving along the x-axis. So you're driving east, but then when you return home, you're driving west. So that would be a negative speed according to this convention. And since you're going from 60 kilometers to 0 in an hour and a half, that means your average speed for the return trip was minus 40 kilometers per hour. So that's how you get average speeds, and there's a couple things you should notice. So the speed is just the slope of each of these line segments, but there's something else interesting about this curve. What if you wanted to calculate the distance you've moved as a function of time? Well, then what you can do is you can get that by just computing the area under this curve. So for instance, the distance you've gone from 9 a.m. to 11 a.m. is just equal to the area of this triangle. And that's half the base times the height. The height in this case is 30. The base is 2. So 1/2 times 2 times 30, that's 30. And that's exactly right. You've moved a distance of 30 kilometers during that interval. Pretty neat. So, and then well, actually, I'm doing this wrong. This isn't a graph of speed. This is a graph of distance. But, and now if you had distance versus time graph, yeah, this is the same kind of idea. Distance is just, well, it's the integral of speed times time. That's what I was trying to say. This is distance. Yeah, I think what I was saying was right. So your speed here, if you look at, yeah, so I wasn't wrong. I was right on this picture. your speed for the first leg of your journey is 15 kilometers per hour, and you're driving for 2 hours, and that means you've driven a total of 30 kilometers. But then, um, um, I don't know. I'm getting a little confused here, but anyway, I mean, this is just another picture that's kind of like the previous one. So here's a bunch of profiles of different types of trips you might take. The first trip, you're moving at constant speed. Constant speed just means constant slope. So in the green line just refers to a trip with a constant speed, and then the blue trip, you've got three intervals, each constant speeds on each interval. But it doesn't have to be constant speeds over interval. It could be a varying speed. It could be a smooth curve like this red curve. And then if that's the case, then if you were trying to calculate how far you've traveled in terms of your speed, you have to do something kind of tricky called an integral. And I'm just going to finish by explaining these two formulas here. So this is where calculus comes in. So remember, I define your average speed as delta S over delta T, where delta S is the distance you've traveled in a given time interval. Delta T is just the interval. If you let delta T go to zero, meaning your intervals get smaller and smaller, you can take this limit. And remember, I was talking about limits yesterday. Limit is a key notion in calculus. So in order to find what a derivative, velocity is actually, or speed, I write as v here. Yeah, speed is a derivative. It's defined as the derivative of your distance that you've traveled with respect to time. And what that really means, it's a limit. It's a limit of delta S over delta T as delta T goes to zero. That's a definition of this derivative. And that's the definition of instantaneous speed. So instantaneous speed is an example of a derivative. That's why we have to use calculus when we're working with varying quantities like speed. And, calculus is used all over the place in the sciences, especially in physics, where you're dealing with motion, things like speed and acceleration, because those are defined to be derivatives. And then there's another formula. What if you want to get the total distance you've traveled in terms of your average speed? Say your average speed is a function of time. This is what I was trying to explain in terms of areas under the curve. So this formula is what's called an integral, and an integral is really just a fancy way of saying the area under the curve. So imagine you had a graph of your speed with respect to time, and you want to calculate how far you've traveled from time t1 to time t2. The way you do that is you calculate the area under the graph of v of t from t equals t1 to t equals t2. This area is called an integral, and this is the formula for it. And these two formulas are really the same formula. It's kind of weird. This is a consequence of a very important theorem in calculus called the fundamental theorem of calculus, which basically says that derivatives or integrals are the opposites of each other. Sometimes people call the integral the antiderivative. If you know one, you know the other, basically. Anyway, that concludes my talk on speed. Thank you for watching. I hope this wasn't too confusing. Long live math, and I'll see you guys next time.